In sklearn, there are two types of functions. One is called support vector classification or SVC, and another is support vector regression or SVR. So in SVC, there are several parameters, and I think there are five more most important parameters, which is C, kernel, degree, and gamma. So let's see one by one. So for example, which is already discussed, let us say there are two-dimensional data x1 and x2, and there are two types of data points which are belongs to +1 and -1, and you have to separate or classify those two types of data points. So you can see that the hyperplane which is separating red points, which is denoted as wx plus b equal to 1. So you can think of this equation as y equal to mx plus c, where y equal to +1 and mx is w and x vector here, and plus b is plus c, and here wx plus b equal to -1 because these points are belongs to -1, and the lines through which these points are going, which is called support vectors, which is already discussed. And you can see that there are 2 points, one is green and one is red here, which are misclassified. So this jitter denotes how much a misclassified point is further away from correct hyperplane in incorrect direction. So you can see from this picture that this green point should be here, but it is in incorrect direction. So zeta says how much a misclassified point is further away from the correct hyperplane to the incorrect direction, and this distance is 2 divided by w, and w is the normal to the plane. So if you take any point and you want to calculate from the distance from this point, so you have to take perpendicular to the point to the hyperplane, so which is unit vector, so which is w divided by magnitude of w, and this r plus r is 2, that is why this margin is 2 by w. So now the cost function will look like, so you have to take the best w's and b's for which this margin is maximized and this errors number of errors are minimized. So you can see from this equation that wb equal to argmax 2 divided by w plus c into 1 by n into summation over all jitters. So in words, find best w's and b's which maximize the margin 2 divided by w or magnitude of w between classes, and this term denotes minimize the average number of misclassified points. So average, why? Because that is why 1 divided by n, where n is the number of data points and zeta denotes it. So here we have already discussed w is the normal to the plane, and c is the, and here this c is the regularization parameter which tells about the trade-off between bias and variance, and zeta tells, which I've already discussed, how much a misclassified point is further away from the correct hyperplane in incorrect direction, and if zeta greater than equal to 0 for all misclassified point. So here the objective is to minimize these jitters or to minimize the summation of the all jitters. And you can see that in this equation, if this c is large, so it tendency to make mistakes minimizes to on retrain. So it actually it is the tendency to make mistakes minimizes on retrain, so it is called high variance, that is why it is called overfit. So if c is large, your model is overfitting, and if c is low, it means high bias, so it will underfit your model. So you can think of lambda 1 or lambda 2, L1 or L2 in this in the previous lasso and ridge regression as C. So next is kernel RBF. So and this is a kernelization trick. So you have already discussed that there are several type of kernelization trick. One is linear, polynomial, RBF, sigmoid, and pre-computed. So and in this example we will see the RBF kernel. And in one line, what kernelization do is it actually transform a data point from d dimension to d dash dimension, where d greater than d less than d dash. So you can see from this picture, which is already discussed. So if there are two types of 2D data set and you can't separate it with a linear margin, so what kernelization will do is actually it will transform to a 3 dimension on which you can easily separate those two types of classes. So what kernelization do? It actually transform d dimension to d dash dimension, where d dimension is greater than d. So this is the kernel trick or feature transformation which is implicitly done in kernelization. And you can see that in RVF, this is the formula. So let's say there are two types of features, x1 and x2, and the data points are scattered like that. So formula of the RVF kernel is, you can think of k of x1 and x2 equal to e to the power minus x1 minus x2 square divided by 2 sigma square. So x1 minus x2, you can think that it is a Euclidean distance, and k means similarity between those two features. So if you and you can think those x1 minus x2 whole square as a distance between two features. So you can think that distance between x1 and x2. So if you put d equal to 0, it means similarity between x1 and x2 is 1. And if you decrease the d, k will increase exponentially. You can check that by substituting different values of d or this term x1 minus x2 whole square. So if d of x1 and x2 or k of x1 and x2 is large, it means k equal to 0. If distance is very large, then k equal to 0. So it says that distance is very large. So you can see that, and this sigma determines the size of this curve. So if sigma is large, the spread of this curve will be large, and if sigma is low, the spread will be minimum. So you can relate it to variance. So if the variance is large, the spread is large, and if the variance is low, the spread is low, and sigma does the same. So here this gamma term in scikit-learn denotes the sigma. So here there are no direct sigma, but gamma equal to 1 by this 1 divided by 2 sigma square is gamma, and which is there in scikit-learn. So by default there are default equal to scale. So if kernel coefficient is RBF, poly and sigmoid, then you have to use this gamma function. And if you take this auto, if you just write gamma equal to auto, then it will automatically figure out what is the right gamma automatically, right gamma for this problem. And so kernel is there degree. So third one is degree. So if you use only polynomial kernel, so if you recall in first lecture, so there was a polynomial kernel d, so 1 plus x1 x2 to the power d. So here d is the polynomial or degree. So degree of the polynomial kernel function is d. So if you only use polynomial, then this degree parameter will be used and ignored by all other kernels. And those are the important parameters, and these are the hyperparameters like c.
So can you repeat the previous one again?
This one or this one?
Yeah, you said the polynomial.
Or polynomial. So what happened is, so in polynomial kernel means, suppose you want to transform the 2D space into 3D space. So here degree is 3, intuitively speaking degree is 3. Suppose there is a quadratic equation, so 1 plus x1 plus x2 to the power 2 3 or 4. So 2 3 4, this is the dimension or degree of the kernel. So to which dimension you want to transform your feature space. So if you want to 2D to 3D, then d equal to 3.
So, sir, kernelization is also like polynomial regression or deep learning like that. That is also a type of kernelization, right?
Yes, there are several type of kernelization like linear, polynomial, RBF sigmoid and pre-computed. So pre-computed means you can also define your own kernelization function. That is, then you can use this pre-computed function. And there is
So sir,
polynomial. Yes.
sir, kernel we can only use in classification statement, or we can use it in regression statement also.
So I think for classification it will be very useful. And if you see this regression, there are SVR, you can see, and there are this kernel equal to RBF. You can also use this RBF polynomial. Same features are there. RBF polynomial in scikit-learn implementation. But in classification, I think this kernel function will be more important to use.
Okay.
Is it okay? So those are the parameters. One is C, kernel, degree, and gamma. And similarly, this there is another class called SVR. So you can go through that, and the parameters are more or less same: kernel, degree, gamma, etc. So here the problem is face recognition or classification task using SVC. So here in this data set, there are several various public figures. For example, this George W. Bush, and then Colin Powell and Tony Blair. This type of faces are there, and you have to classify those faces according to to their name. And we want to use it. We want to do it using SVC. So, as an example, support vector machine in action, let's take a look at the facial recognition problem, and we will use the labeled faces in the wild data set, which consists of several thousands of collected photos of various public figures. So for that, first you have to import these libraries, and then you just call this import this. Actually, this dataset is already there in sklearn.dataset, so you just import fetch underscore lfw underscore people. So automatically it will be imported. And if you want to see the names of the figures, then you just print it, and there are several names like that. And this is the size of the data set. And you if you want to print some photos, then you can print it. So I have printed four images like Colin Powell, George W. Bush, etc. And now what we have done is we have used principal component analysis. So what principal component analysis do is, actually it will take the top or most important features from this image dataset, because it will help to train faster. That is why this principal component analysis is used here. And there are a class called randomized PCA in sklearn, and it uses some SVD, or singular value decomposition, to take the most important features from the image dataset. Actually, this image is a matrix. So using SVD, it will first decompose it into three U, and then there will be a sigma and V, where sigma is the um, sigma or the summation, which is diagonal, and U and V will be the orthogonal matrix. And from that, it will automatically take the most prominent or most dominant features from the image matrix, and it will train the model. So for that, we have used principal component analysis to extract 150 fundamentals components to feed into our support vector machine classifier. For that, you just import SVC and then randomized PCA, and then this make pipeline to both to make the to make use this PCA and SVC in a same pipeline. So from this code, you can see that PCA is an object of this randomized PCA, where I have used n components equal to 150. It means it will take 150 most prominent or dominant features from this image matrix. And white n equal to true, it means it will do some I mean reduce the image size by doing white n equal to true. The image size will be reduced, and random state equal to 42. And then SVC equal to SVC, here kernel equal to RBF, RBF kernel is used, and class weight is equal to balanced means if dataset equal to dataset is unbalanced, then it will automatically balance it. And then the model is make pipeline means it will take SVC and PCA both these. So here the line you can see that principal component analysis is used to feed into our support vector machine. So both those computed this pipeline, and then we have just splitted the data into test and train, and then the hyperparameter tuning step. So as we already see that seen that there are several hyperparameters, and C and gamma are most important. So for that we have used as usual grid search cost validation to explore several combination of these parameters. And we have already see that C is the parameter which controls the margin of hardness, and gamma which controls the size of radial basis function. So here gamma
Sir,
is, yes,
sir, I have a doubt in principal PCA, sir.
yes.
Sir, even for same class, like for example, if two images are of George Bush only, but can we like when we are doing PCA for each of these two images, then the features extracted may not be related, right, sir? So how are we doing it?
Yes,
Uh,
yes. Actually, here in this example, it is showing very good result. But in real world, I would say you do without principal component analysis and with principal component analysis, and you just see which one is the best, and that will be the best case for
yes, sir. Uh, Sir, in general, I have heard that PCA is very useful, but I am still not very convinced that where all it will be useful. So, can you just tell some areas where PCA is useful, sir? Like from your experience.
So I think actually the main reason behind this example I have used PCA because the time for this code to run will be very low, and if you use without PCA, then this training time will be very high. And this is just I think demo purpose, that is why I use this PCA. But if you want to actually use your model into real world, then I would suggest that you just take both PCA and without PCA, and you just see which one will be the best. And PCA is mostly used in the face detection, and there is a feature, there is a term called eigenfaces. So in eigenfaces, what it does, it just classify the faces using the most dominant eigenvalues. So and actually PCA is used in this area most prominently in eigenfaces or image processing tasks, where the dataset will be very large if you take all features of the dataset. And if you take PCA, some features like I have used here, 150 most fundamental components, then this dataset will be very low, and I can train this model using less time.
Yes,
So
sir. Sir, so
Sir,
building on this, sir, one more doubt. So, sir, if the face is partially visible, for example, say George W. Bush was standing behind a wall. So, if we
yes,
do PCA there, will it be useful?
yes. No, I think not, because if in image there are several objects, walls, and suppose there is a tree or there is a bus, like that, then if you take PCA, then it will not give the best result. And it is the and you have told the right thing, I think.
Sir, one more thing. So, if George W. Bush's face was not, like, say he was standing, say his only left part of his face was visible, uh,
Yes.
not obstructed. So, but the images in that particular angle. So, will PCA be useful in that sense?
Actually I would say not, because I didn't do it. But from my experience, I will say that it is better not to use PCA there. So
Okay, sir. Okay. Okay,
actually
understood.
and in this example, you can see from this result, this is a funny result, because in confusion matrix you can see that using PCA there are 11 images which are actually of George W. Bush. It is saying that it is for of Colin Powell. So you can see that from this result. And I think if you don't use PCA, this accuracy can be minimized, I think.
Okay, sir. Okay, okay.
So PCA works for taking all the images and then calculating the features, right?
P- uh, Actually,
I mean,
yes.
it take all the features from all images into rows of different images, and then it uses PCA, right?
So
So otherwise we cannot get.
actually in PCA can be done in two ways. So first one is you can suppose there is a here this image, there is a matrix image and their size, if 0 to 255, the size of the matrix will be 255 into 255. And then if you use this randomized SVD PCA, it will decompose it into SVD and it will take the most prominent features. Here there is a and one another approach is there, where it just decomposed it in a eigen values. So it will take the top eigen values and it will take the corresponding eigen vectors, and then it will take those top features. I mean, how many number of sub component you want to use. So and this task will be done on covariance matrix. But here if you use this randomized PCA and if you use SVD, then it will be done on data matrix. There is a difference. So if you use SVD, then it will be done on data matrix, and if you do principal component analysis on eigen values, then it will take the covariance or correlation matrix. So but the fundamental intuition is same. It will take the most prominent or most dominant features from the matrix, or most actually, if you simple suppose there is a matrix 3 by 3, and if you calculate the eigen values, suppose there is a lambda 1 equal to 5, lambda 1 equal to 4, and lambda 1 equal to 3, and if you take this n components equal to 2, then it will take the most two, lambda 1 equal to 5 and lambda 1 equal to 4, because 5 4 3, and most and the two maximum values are 5 and 4, and the eigen vectors which is corresponding to 5 and 4 will be taken. That is how it is calculating. And here this 150 fundamental components means that in that sense. Is it all right? Or
Yes, sir. Okay. Fine.
okay. So now in this hyperparameter tuning step, so we have just taken several values of C and several values of gammas. So you can see that from in C 1 5 10 50, and gamma is taken 0.0001 0.0005 like that. And then we have taken this grid object, and in this grid search cross validation we have taken this model, and here this model which is make pipeline PCA SVC and this parameter grid, and then fit it. And if you print this grid dot best params, it will show that the best C is 10 and best gamma is 0.001, and on that we have predicted several images. For that we have used this function, and in this, and the significance of this function is, if this image if the prediction is right, it will print it as black, and if prediction is wrong, then it will print as red. So you can see from this picture that there are 1 2 3 4 5 6 24 pictures, and there are most of the pictures are correctly classified, but there is a one picture of George W. Bush which is misclassified as Blair. So, and if you see the whole data set, it will see it looks like, and you can see from this classification report that for each and every person there are some precision recall F1 score, and the accuracy is 85%. And I would suggest to do it without PCA, and you can see the accuracy. And for on that model, if you see this confusion matrix, you will see that there are most of the points are correctly classified because diagonal element is very high, but there are 11 data points which are actually of George W. Bush, but this model is telling that Colin Powell. So here is the example. You can see that there is a George W. Bush, but it is saying that Blair. So that is the uh, meaning, I think. So that's it. So now you have, if you have any question, you can ask.
Sir, can you give an example of a support vector regressor where we can use the kernels?
Oh, okay. So let me go to this site, SVR. So you can see that, and there are SVR. So SVR, there are several parameters like RBF, degree, scale, like that, and for that you can see in any sklearn. If you want to see any module, you just go to this leftmost page. You will see different example of these examples, for which in which regression task SVR is used. For example, there is a problem called prediction latency. For that, they have used SVR. So, and there is a called comparison of kernel ridge regression and SVR. And like that, there are several types of um, regression tasks. And I think there are several tasks in which you are using linear regression. You can also use SVR to see which one is the best. And I think and it will be not easy for me to specify the best problems in which you can use SVR. But I would suggest, if there are any regression problem, you just use linear regression, lasso ridge, and simultaneously use this SVR. And for any model in machine learning, you just and from going one model to another model, this is just one line change, and this is this line change. So I think SVR, where is SVR? So this is SVR. So you just call this extra line from sklearn.svm.svr, and then you just this call this line regression equal to make pipeline standard, like an SVR this. And for linear regression, you just you will find that there are another class name, and you will just take this object and call this lasso or ridge regression and fit it and see the accuracy, and you will automatically see which regression is the best.
So this pipeline is only for sklearn modules, right?
Yes, as of my knowledge, I think pipeline is used in this sklearn, because I have extensively used a sklearn, but I didn't use any other library, machine learning library, I think. So and make pipeline is useful because if you um, want to use several, for example, in my example, I have used PCA, and then we have used SVC. So for that purpose, it is very useful. So you just distinctly or separately do your models PCA, run on it, and then you just run on SVC, and just merge it using make pipeline, and then you just use your grid search cost validation in another module, and then merge it, and then run and then fit your model onto it, and then calculate the accuracy confusion matrix. And for those, I think make pipeline is very useful.